afternoon. I'm David Hallac, and I'm joined by Nick Howarth, Sam Wolfson, Cam Cogan, and Ashleigh Thomas. And our project is the Primate Hand Actuation Tracker, or PHAT for short. So, a big question today in neuroscience is which neural signals map to given hand motions or outputs. That is, say I want to move my finger as such. Neurons in my brain will fire, sending a signal through my nervous system to cause an actuation in my hand muscles to do the commanded output. The work of Dr. Timothy Lucas, a professor in the medical school here at Penn, is trying to develop this map to find precisely which neurons and which parts of the brain map to which hand outputs. Within this large body of work, our project, PHAT, focuses on one particular aspect, measuring and analyzing the hand motions. In this particular case, hand motions of a rhesus monkey. So, plenty of motion capture systems exist out there, but due to the context imposed by this project, they are not sufficient for this case. Electromagnetic field sensors detect changes in an artificially generated electromagnetic field. However, due to their nature, they introduce noise at a frequency less than 10 kilohertz, which is the same frequency that the simultaneous brain mapping is going to occur, which will interfere with these brain reading results. On the other hand, vision-based systems such as Vicon are very popular. However, they are extremely expensive, costing upwards of tens of thousands of dollars. And furthermore, solely using a vision-based camera system, beacons and visual cues on the hand are subject to becoming obstructed for certain hand configuration. For example, when I clench my fist, any cues on my fingertips are out of sight of any and all cameras, which can lead to an inaccurate reconstruction. So, this gap in the market is exactly where PHAT comes in. What we built is a motion capture system designed for Dr. Lucas and other researchers like him to perform their testing. This research tool tracks 20 degrees of freedom in a humanoid hand. Furthermore, it does not introduce low-frequency noise, so it can be used in conjunction with neural recording equipment. Finally, it was designed to be tested and implemented on live monkeys. So to create this system, we decided to use an innovative two-pronged approach that, to the best of our knowledge, has never before been attempted for the purposes of motion capture. We're taking two independent data streams. First, from a series of inertial measurement units, or IMUs, placed on various points on the hand. Secondly, from cameras in this rig, combining these data streams. The key is that the two streams have very complementary strengths and weaknesses. The IMUs have a fast sample rate and can detect slight changes in motion. However, because they have no global anchoring system, they're subject to something known as systematic drift. So over time, their results get more and more inaccurate. On the other hand, cameras are a little bit slower and can only detect fewer beacons at once. But because they have this structural setup here, they're very good at, in an absolute sense, determining where in three-dimensional space the beacons they're tracking are. So from start to finish, our motion capture system uses a 5-step process. First, we acquire the data via testing. Then, after the test is complete, we independently process the two data streams. Then we combine them via something known as a Kalman filter. From there, we have one unified hand output, but we perform inverse kinematics to convert that into individual joint angles and joint positions. Finally, for verification, we use a wireframe visualization to see our results. Now, Ken's going to talk about how we gather the data.
Great. Thanks, David. So, naturally, the first step in constructing this 3D model of the hand is acquiring the data necessary for that reconstruction to take place. Our first means of doing that is with this grid you see beside me. Constructed out of PVC, we have 3 cameras mounted here, here, and here. Now, each of these cameras is very tightly synchronized, allowing us to use the footage from one camera against the footage from these 2 companion cameras. While only 2 of these cameras is necessary for placing the beacon in 3D space, just as we do with our eyes, we chose to use 3 to maximize our coverage of the hand, thereby minimizing the chance that we lose any given LED. Now, these LEDs are located on the glove on my teammate Nick's hand here. During any given trial, what you'll typically see is a green LED that will stay on until it receives a signal from the microcontroller controlling the entire globe. When that happens, the beacons will oscillate at a frequency very closely tuned to the frame rate of our cameras. This oscillation allows us to only track half the LED beacons on the hand in any given camera frame, thereby expediting post-processing. While that's all taking place, the IMUs on the hand will be collecting information about angular velocity and linear acceleration. Any given test trial will look like what you see above. In this video, you'll see an angle from the overhead camera here of a hand engaging in a clenching motion. Footage like this is accumulated from each of the 3 cameras in a given perspective, and then fed to our video analysis software, which you can see in action here. Now, as you'll see, as I mentioned before, in any given frame, only 3 beacons are visible. The gray circles that you see overlaid on top of the original footage, which is taken from the same video that we just saw, signify matches that the software has found against beacons in the 2D frame. This 2D information is accumulated from each of the 3 perspectives and then combined using a 3D localization technique that functions as follows. Mathematically, a ray is cast from each camera's perspective through the beacons on the hand. This process is repeated for each beacon, for each camera perspective, and where the rays meet or come closest to meeting, we record a 3D position in space. This process is repeated for each beacon, for each frame in the trial, until we have a comprehensive set of information about each beacon's location over the course of the trial. That sums up how we retrieve information from the camera rig. I'll now turn things over to my team Sam to discuss the process of extracting information from IMUs.
Thanks, Sam. So we're trying to use the IMUs to track the linear motion of each fingertip. Unfortunately, the accelerometer has no way of distinguishing between acceleration due to gravity and acceleration due to the motion of the finger, as you can see in this picture. So the raw data from the IMU has a constant offset of 1G, which you can see in the top plot up there. Unfortunately, that 1G is not consistent in each component. So depending on the orientation of the IMU, that 1G is going to have a different weight for each component. So to solve that problem, we use a sensor fusion algorithm to combine the data from the gyroscope and the accelerometer to get an orientation at each timestamp. We use that orientation to figure out just how much gravity needs to be extracted from each component of the accelerometer vector. And that results in dynamic acceleration, which you can see in the top plot here, which is the acceleration just from the motion of the fingers. We then integrate that using a numerical integration algorithm to give us linear velocities, velocity of each component in free space. And that's the data that's fed to the Kalman filter, which Ashleigh will talk about now.
Now that we have 2 reliable data streams, we need to integrate them into one cohesive model, and we do that using a Kalman filter. First, we create 2 separate predictions of the locations of each of our 6 beacons. One prediction is based solely on IMU data, and one prediction is based solely on camera data. Then we take a weighted average of these 2 predictions to get our Kalman filter output. Now, the filters in the weights in the filter are based on our certainties on each of our measurements. As I said before, one of the benefits of using cameras is that they're very accurate. So we make our camera prediction weight much heavier than our IMU prediction weight. One of the benefits of our IMUs is that they update much more quickly than our cameras. So when we don't have any camera data, we can still use the IMU prediction to get a Kalman filter output. Now you can see the same data that we've been following throughout the presentation after it's gone through the Kalman filter above. To the left, you can see an overhead view of our clenching motion, and in each of the blue circles, you can follow the trajectory of the finger as it curls underneath. To the right, you can see the same data in 3D representation from the side. Now, the output of the Kalman filter is not a full reconstruction of the hand. To get that, we go through a process called inverse kinematics. We use the Kalman filter output as well as the lengths of each of the bones in the hand to calculate the angles and positions of each of the joints in a humanoid hand. This is our final data output and is ready to be directly compared to neurological data. To verify our system, we've also created a 3D wireframe rendering of a humanoid hand. Here you can see some synthetic data following a similar grasping motion to before from a few different angles. Now that we've gone through the flow of our system, Nick will wrap it up for us.
Thanks, Ashley. So what we presented here today is an innovative approach to motion capture. Using some pretty sophisticated processing, we were able to successfully integrate 2 independent streams of data, one from the cameras and one from our IMUs, into one unified model of a hand. Now, our system has 2 key advantages over the state-of-the-art approaches in motion capture that are used today for this application. Namely, 1, they do not introduce any electromagnetic noise into the neurological recording spectrum, which is anything below 10 kilohertz, which is very important because the purpose of this system is that it is to be used in conjunction with neural recording equipment. So we do not want to introduce any noise into the neural signals. Secondly, our system is relatively inexpensive. The total system has a cost of less than $2,000, which is at least one order of magnitude cheaper than the state-of-the-art systems today, which would cost upwards of tens of thousands of dollars. More importantly, our system is modular, and so each component by itself is pretty inexpensive. So if one part does break, then it can very easily be replaced. And this is important because we are testing on live animals, so this kind of thing can happen. Now, we're very happy with the results that we've seen so far. They look very promising, but the ball does not stop rolling here. We have a few ideas on how we can continue this project and improve our results. The first step is to use something like an FPGA or a programmable system on a chip instead of a microcontroller. Right now, we're using a microcontroller to talk to each of the IMUs one at a time, and these are latent operations. So using an FPGA, we would be able to pull from each IMU in parallel, and this would allow us to greatly improve our sampling rate and fill in more gaps between the camera frames. Second, if we had more cameras on the rig here, we would be able to increase the visibility of the hand. And third, we need to improve the durability of our system. So this is something that will be tested on live animals, so it needs to be durable and used over many months. So a few ways to do that, we would, obviously these wires would be bound down, tied into the glove. And we could coat the IMUs, the inertial measurement units, with something like an epoxy to protect them from physical contact. So again, we're very happy with what we've seen here, what we've seen from our project. We had a great time working on it, and we'll be happy to take any questions now. Thank you.
You said something about blinking, the lights blinking. Can you repeat that again?
Yeah, maybe just take that. So the scheme that we have right now is that we have 3 colors of LEDs on the hand across 6 different PPs located there. To allow us to not have to worry about 2 red LEDs in any given frame, differentiating which of those LEDs corresponds to which finger, what we do is oscillate the LEDs. So in a given frame, you only have 3 out of the, you have 1 LED in each color, but only 3 out of the total 6 LEDs on.